right, hello, Jalen. This is the second half of 1.5 notes. 1.5. Let me make sure that that's true. 1.5. Okay. Second half of the notes. We're starting right above example 5. All right. Here we go. Put a star by this.
A star?
If you're talking about an inverse function, inverse functions undo one another, right? An inverse function undoes the original function. If the original is continuous, the inverse is continuous. So it says the inverse of a continuous function is continuous. If the original is continuous, the inverse is continuous, okay? So like a function that undoes x to the third power is going to be some form of the cubic root of x, right? I don't know why it's doing that.
So it becomes just x.
What?
What?
Yeah. So the deal here is, so these two functions are inverse functions of one another. They undo one another, right? If you stick one inside of the other, it's going to be, it's going to have more on it than that. It might be like the square root of x plus x. I don't know what it is. It'll be more than just that. But like the root or just an x cubed function, his inverse will be just the cubic root of x. Got it? Okay, and if he has more on him, we have to like find the inverse, and it's a little bit harder. But it says show that the function has an inverse. Its inverse is continuous at each point. Is its inverse continuous at each point? Okay. Show that the function has an inverse. Okay. How do they want me to show that it has an inverse? I don't know. Let's look at this. This is my function right here. I'll do this a couple different ways. I don't know how they want me to do it, but we'll do it a couple different ways. So x cubed plus x, that's the graph of this guy. We know that he's an x cubed function, okay? If I do what's called the vertical line test, that tells me that he is a function. That tells me that he is a function, yeah? He is a function. Okay, now, have we done the horizontal line test ever before?
Yeah,
Okay, so
point intersects 1.
my function, x cubed plus x, this is the original guy. The vertical line test, I'm going to do VLT, check. That means yes, he is a function. He is a function.
What?
He is a function. Okay, now, if I take the original, which is x cubed plus x, and I do the horizontal line test, that means his inverse is a function. Okay, so if I do the horizontal line test, does he check out?
Yes.
Yes, that means he will have an inverse. True? Okay, and his inverse, I don't know. And his inverse is going to be some form of x cubed, or the cubic root, excuse me. I don't know. I don't know. Okay? His inverse will be some form of the cubic root of x, and it will be a function. So
Inverse will what?
the inverse will be a function as well. So show that he will have an inverse. Yes, he does because of the horizontal line test. He has an inverse. Okay? Is the inverse continuous?
Yeah,
Why?
because it works on the horizontal line test. Oh, maybe not. I don't know.
Maybe.
Wait, why is he?
He's a function, but not all functions are continuous, right?
Yeah.
So he has a function. His inverse is a function, but is he continuous?
Okay, so what are
How do I judge whether he's continuous or not?
If he has a hole.
Nope. The inverse is a function if the original is the inverse is continuous if the original is continuous.
Oh.
Is the original continuous?
Yes.
Yes.
The
So is the inverse continuous?
Yes.
The inverse is continuous, yes, because the original is continuous. So he has an inverse because of the horizontal line test.
Can we just look at the graph and if it's
Right.
Yeah.
I mean, yeah,
If it-
kind of.
If
I mean,
it has
if it's-
that,
Yeah.
if it like doesn't have a hole in it, just is.
Right. True.
What is it if it's not a function? What is it?
A relation. Yep. Yep.
But
Don't worry about that.
You said not every function is continuous.
Right. Like piecewise. A piecewise function is a function, right?
But it's not continuous.
A piecewise function is a function, but it's not continuous.
Yeah.
Because a piecewise function will pass the vertical line test, right?
Because it doesn't matter if there's a hole in it.
Right. It doesn't matter if there's a hole.
But it
It
wouldn't pass
just
the
doesn't want it to
vertical.
repeat, right? Yeah. So we just want to make sure an inverse is only a function if the original is, an inverse is only continuous if the original is continuous. Okay. All right. Let's talk about this. The intermediate value theorem. This is kind of hard to understand, but it is kind of a stupid concept. Okay. Are you ready for this?
No.
first things first. If a function is continuous, if a function is continuous, it has to be a continuous function,
Continuous.
okay? If a function is continuous, and let's say the y coordinate up here is at like 6, and the y coordinate down here is like at 2, then that means that somewhere here in the middle, it has to hit at, let's say, 3, or 4, or 5. Doesn't that sound stupid?
Yeah.
Okay,
I'm so
now,
confused. Wait, so it just has to hit.
if it's a continuous function and they tell you what the
Oh,
upper
okay,
limit
yeah.
is and they tell you what the lower limit is, as long as it's continuous, we know he has to hit at every single place in between, right? Okay, so we're going to expand that to something called the mean value theorem, which I don't know is maybe on the backside. No, nope, they don't even say the mean value theorem. All right, intermediate value theorem. So we're going to use that, and I'm going to talk about this little diagram down here. So the best application of the intermediate value theorem says that, let's say we have that this is y equals 1. That has a y coordinate of 1. So something comma 1. We don't care what it is. Something comma 1. And this guy down here is something comma -3, right? So his y coordinate is -3, and this guy's up here is y coordinate is 1. We know, because he's continuous, that there has to be a place where the y coordinate is 0, where he's going to cross the x-axis. If one place is above and one place is below and he's continuous throughout, he's got to touch at some point, right? That only makes sense. That's what the intermediate value theorem is illustrating. Make sense? Yeah? Ish. Okay, so let's go through the example. Example 6, the equation. This is a cubic function, and I think that's what's graphed right here. But we're only graphing it from A to B. So this chunk to this chunk. We're only looking at that little sliver of it. We're not looking at forever to the left and forever to the right. We're only looking at that little chunk, okay? It says cannot be solved algebraically very easily because the left side has no simple factors. We can't break this down by factoring. You trig kids, we can't break that down by factoring because it doesn't factor very nicely. So what we do instead is we start pinching him in and in and in. And we say, okay, let's say that this is at 1 and this is at -3, right? Let's say it's at 1, 1 and at 6, -3, right? Okay, let's say 1, 1 and 6, -3. I know that he's going to have a 0 somewhere between 1 and 6, right? On the x-axis, because the y's are going positive to negative. So he's going to have a 0, or he's going to cross the x-axis somewhere between 1 and 6. And then I can keep pinching that in. I can say, okay, let's come over here to where it's at like 3, 1, and let's go over here to where it's like at 4, -1, right? I've pinched it in even further. So if I keep pinching it in, now I can conclude that where's my 0 going to live?
In between.
Somewhere between 3 and 4. Do you see that? I can keep pinching it in and I can figure out from the intermediate value theorem, because he's a continuous function, I can keep pinching that in and say, okay, since this one is above and this one is below, I know that there's going to be a 0 somewhere between them. Does that make sense? Yeah, I can continue to do that, okay? So we're going to approximate this root to 2 decimal places. All right, so let's go to this backside here. This is what the actual graph of it looks like. This was just an illustration, so that's my example. This is not the actual function. That's not the graph of what this is. We're going to actually do the problem down here. And here we have, all right, so we have the graph of x cubed minus x, and we know that he's crossing about right there, right? So I could say that he is going to cross somewhere between what and what?
1 and 2.
1 and 2, but I want 2 decimal places. So what I did was I looked at 1 and 2, and I did 1 decimal place, right? This table is going out to 1 decimal place, okay? So now, going by 1 decimal place, where is he going to be between? 1.3 and 1.4. Do you see where he switches from positive to negative there? Okay? Then, now that I know it's 1.3 and 1.4, I'm going to put 1.3 over here and 1.4, and now I'm going to go 2 decimal places. Now, if I go 2 decimal places, now where is he going to be between? 1.32 and 1.33. Do you see that? That's where he switches from positive to negative. So using that concept of the intermediate value theorem where he switches from positive to negative, I can keep pinching him in closer and closer to figure out that he has a 0 somewhere between 1.32 and 1.33. Does that make sense? Somewhere between those two. Does that make sense?
I just remember, like, that's our answer.
Yeah. Yep, so we use those tables to kind of like pinch him in a little bit closer, right? Okay, so we started off knowing that from the graph that it's somewhere between 1.1 and 1.2. Then we used a table to kind of like do one decimal place, found those two values, and then we put those here and here to find two decimal places, okay? Now we could continue on if we wanted to. I don't want to, but if we wanted to, we could continue on and do another one where we're going 3 decimal places. So I could put 1.32 here, 1.33 here, and put 1.321 and 1.322 and 1.323, and I can figure out where he's gonna live between there. Does that make sense? Okay, I could keep going on and on and on forever and figure out where it switches, and that's gonna be where he's at, right?
Reminds me of counting
Okay.
measures in band.
Good? So that's the intermediate value theorem. He says he has to have a 0 in between these two values. Got it?
Or marching.
Okay, that is it. That's continuous. That's continuity. Woo! Happy with
Well,
that?
we haven't really marched.
Yeah.
All right. There you go. Use the rest of your time to work. We got lots of time, actually.
It's like before school.
We would have a lot more time if we didn't take.
We would have had a lot more time if we didn't argue for 20 minutes. All right. Goodbye, Jalen.